Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. For a 6-membered ring compound to tautomerase to an aromatic product, it needs to convert to benzene, all-carbon, or a heteroaromatic compound, like pyridine, by proton transfer. This requires the non-aromatic tautomer to have the right number of degrees of unsaturation and the correct arrangement of heteroatoms or functional groups such that moving a proton yields a fully conjugated aromatic ring. Analysis of each compound. A. 1, 2, 3, 6 tetrahydropyridine 4, 1H, 1, shown with NH, C is equal to O, and 1C is equal to C in the ring. This is the keto tautomer. The enol tautomer would involve the NH proton migrating. If the NH proton transfers and the C is equal to O becomes CO with full conjugation, the ring can achieve a pyridine 4-ol is equal to 4-hydroxypyridine, which is aromatic pyridine ring with O substituent. The lactam to hydroxypyridine tautomerism is well established. 4-pyridinone-4-hydroxypyridine. 4-hydroxypyridine is an aromatic compound. So, A. Yes, tautomerases to give aromatic 4-hydroxypyridine. B. Cyclohex 2N1-1. To cyclohexene, this has 1C is equal to O and 1C is equal to C in the 6-membered ring. Enolization of the alpha position adjacent to C is equal to O can extend conjugation. The full enol tautomer of cyclohex 2N1-1 would be phenol C6H5O. If two proton shifts occur to give complete conjugation, actually cyclohex 2N1-1 can tautomerase stepwise to phenol, an aromatic compound, via the dienol intermediate. So, B. Yes, can tautomerase to phenol, aromatic. C. Cyclohexa 2,4-DN1-1, 2, 4-cyclohexadienone. This compound is already one proton transfer away from phenol. Moving the C1 carbonyl O, i.e., enolization at C1 directly gives phenol. This is the classic phenol cyclohexadienone tautomerism. Phenol is aromatic. So, C. Yes, directly tautomerases to phenol. D. Cyclohexa 2,5-diene 1,4-dione parabenzoquinone. This compound has to C is equal to O groups. Its enol tautomers would require both carbonyls to enolize to give hydroquinone 1,4-dihydroxybenzene, which is aromatic. However, parabenzoquinone itself is the oxidized form, and its tautomer hydroquinone is aromatic. But wait, the structure shown appears to be cyclohexa 2,5-diene 1,4-dione p-benzoquinone. For tautomerism to aromatic product, a simple proton shift is needed. P-benzoquinone does not have an acidic CH adjacent to the carbonyls in a way that a single tautomeric shift gives a fully aromatic product. It would require two enolizations. Simple ketoenol tautomerism of 1C is equal to O does not give a fully aromatic ring. So, D. No, does not simply tautomerase to an aromatic product by a single tautomeric step. E. Cyclohex 2N1-1 to cyclohexene, same connectivity as B but drawn as the saturated ring form. Actually, this appears to be to cyclohexene again, a 6-membered ring with C is equal to O and one double bond, fully saturated, otherwise similar to B, but looking more carefully, E appears to be cyclohex 2N1-1 without the extra conjugation needed. A single enolization step gives cyclohexa 2,4-DN1-ol, not directly phenol. Multiple tautomeric steps would be needed. Strict tautomerism, single-step proton transfer, from cyclohex to enone does not directly yield an aromatic compound. So, E. No. F. Cyclobut 2N1-1, Cyclobutene four-membered ring. Even if enolization occurred, a four-membered ring cannot be aromatic, would need to be cyclobutadiene, anti-aromatic. So, F, no. G, 4,4-dimethylcyclohexa, 2,5-DN1-1, the gem-dimethyl group at C4 means that enolization at C4 is blocked, no CH at C4 due to two methyl groups. The compound cannot tautomerase to give a fully aromatic benzene ring because C4 has no hydrogen to lose gain to complete aromatization. So, G, no. H, 4-hydroxymino, cyclohexa, 2,5-DN1-1, paraquinone oxime, shown as 6-membered ring with C is equal to O at top and C is equal to NO at bottom with conjugated double bonds. This compound can tautomerase via oxime nitroso or more relevantly via the C is equal to O enolization. The paraquinone oxime can tautomerase to 4-nitrosophenol or 2-paraminophenol. More precisely, the NO group can shift the C is equal to NO oxime with the C is equal to O can tautomerase such that CO forms and C is equal to N remains, or the ring fully conjugates. Actually, 4-hydroxymino, cyclohexa, 2,5-DN1-1 is the tautomer of 4-nitrosophenol. The quinoid oxime tautomerases to the aromatic nitrosophenol, or via the paraquinone monoxime to 4-aminophenol route. The key point, the quinone oxime, non-aromatic, quinoid form, tautomerases to the aromatic nitrosophenol form, which has a benzene ring. So, H, yes, tautomerases to 4-nitrosophenol, aromatic. Summary: A, yes, B, yes, C, yes, D, no, E, no, F, no, G, no, H, yes. Count is equal to 4 compounds, A, B, C, H. Therefore, the correct answer is 4, A, B, C, H. The correct answer is shown on screen.